From man's earliest beginnings to the present, he has been making and using tools as a means of gaining a more effective control over his environment. These tools in the service of man can be divided into two groups. There are tools that increase man's control through extending his physical powers. And there are tools that increase his control through providing him with new information and new ways of processing this information. This second group of tools consists of machines that literally enlarge our intelligence through their power to manipulate the symbols of arithmetic and logic in relation to real-life situations. Numbers can be used to represent everything from one orange to one galaxy. Models of real-life situations and things can be constructed of numbers. And these mathematical models can be manipulated so that we may extend our knowledge of how to control, design, and predict the behavior of things and processes in the real world. Within the past 2 decades, the digital or number computer has made possible a major advance in our ability to store, process, and interpret the information that man can symbolize within the universe of numbers. Today, computer technology is being taught even in some high schools. Here, Fred Gruenberger of the RAND Corporation talks with research mathematician Richard Hamming of the Bell Telephone Laboratories.
Now, I'd like to show you some of the things that I've been doing, just as an example, in training young people in computing technology. We'll bring in some instructions from the paper tape over there to do a few problems. At this time, we're reading instructions into the storage unit of the machine, which is in here. And when the tape stops reading, the machine is now calculating, and some numbers appear. Now, you'll notice we haven't labeled the routine, because in demonstrating to high school children particularly, I like to let them tell me what's going on. You like to guess?
Well, that's easy. That's powers of 2.
Okay. They're labeled. The 8th power of 2 just came out, 256. It's going up by 1s. Now, a student can readily detect that this is virtually a trivial problem. In fact, he can do this much arithmetic in his head as the machine is running. He can probably run this far. Now the numbers are beginning to get big. Now, if we move a switch here, we've stopped going ahead by 1s, and we're going ahead now by 10s. The numbers are getting big very fast.
Right.
This he might have a little trouble doing with pencil and paper. Let's move another switch. We've just generated the 60th power of 2. Now the 100th power of 2. Notice also now that it takes a little bit more time. The computer is counting for us, bypassing the intermediate numbers, the 200th power of 2, and at the flick of another switch, we'll go a little faster yet. Not only are we illustrating that the computer can do a little bit more, this is still a very simple problem, but can handle extremely large numbers.
Here is a beehive, but where are the bees? Hidden away where nobody sees. Soon they'll come creeping out of the hive. 1, 2, 3, 4, 5.
Very early in life, we begin to learn numbers. It usually begins with counting the fingers.
5.
In fact, if humans had only 4 fingers on each hand, we would probably have a number system based on 8 rather than 10.
2, 3, 4, 5, 6, 7, 8, 9, 10.
All right, place your bets, folks. Round, on you go. Round and round and round. 3. Here we go. There's a lucky number. Yeah, big 5. All right, ladies and gentlemen, once more the lucky wheel spins. Number. Relax, gang. Here it comes. Number. Everybody else loses.
I'll tell you one.
Our use of numbers can be playful and serious, simple and complex. But the perennial problem that confronts most human beings is that we're not very good at numbers and arithmetic. And so, very early, thousands of years before our modern era, man began to invent mechanical aids for counting. One of the earliest of such aids is the abacus, a counting instrument still used in many parts of the world today. Like so many inventions, counting machines have arisen in response to particular needs. The 17th century philosopher and mathematician Blaise Pascal invented an arithmetic machine to help with the boring, repetitive job of making accurate calculations in his father's tax office. This was the first truly mechanical calculator, and it used a basic idea of arithmetic that had been missing in all previous mechanical adding machines, the tens carry idea. Mechanically, the carrying operation means that when the units wheel has advanced 10 steps, the tens wheel advances 1 step. This principle is used, for example, in the mileage counter of your automobile. 32 years after the Pascal machine, another philosopher-mathematician, Gottfried Wilhelm von Leibniz, invented a machine that would multiply and divide. Mechanically, however, the Leibniz machine was not very reliable, and more than 2 centuries were to pass before a genuinely practical and reliable calculating machine was invented. For example, in 1889, Léon Bolet invented a practical mechanical multiplier. Bolet was only 18 at the time. However, the machine was never produced commercially because Bolet devoted the rest of his life to racing automobiles. Today, the mechanical calculator is a familiar fixture on many an office desk. But it is a limited device simply because it is mechanical. That is, parts within the machine must move for every operation performed, and the operator must key in every step that the machine performs. This obviously takes time. If a machine could carry out calculations automatically, remember intermediate results, and print out the final results, the whole process would be speeded up considerably. Just such a machine was designed, but not built, by an English mathematician, Charles Babbage, in the 1820s. Financial difficulties forced Babbage to abandon construction of his difference engine, a machine designed to calculate mathematical tables. But his design incorporated automatic calculation, or sequence control, a mechanical means of remembering intermediate results, and a means of producing results in printed form rather than requiring them to be recorded manually. Babbage's designs were many years ahead of the technology of his time. Only years later was an actual difference engine constructed. A particular need is so often the stimulus for an invention answering that need. But there must also be a technology adequate to the invention. A combination of these circumstances at the beginning of this century produced the now familiar punched card method of data input. The United States Census of 1880 required 7 years to complete. Given the rapid population growth in the United States, if all the data had to be hand-fed to calculating machines, the 1890 census might not have been completed before time for the 1900 census. A Census Bureau statistician, Herman Hollerith, observing this problem, solved it by developing machines which added up the data from holes punched in pieces of cardboard the size of the then current dollar bills. The Hollerith punch card innovation permitted the 1890 census to be completed in 3 years. Automatic calculation, plus the punch card method of feeding in data, represented a considerable increase in speed. But this was still mechanical, or at best an electromechanical system made up of many moving parts, and every instruction had to be placed in the machine at the appropriate time by an operator. Two further developments in concept and technology changed this and introduced an increase in speed and reliability that almost defies the imagination. First, the development of true electronic rather than mechanical or electromechanical machines. The first completely electronic calculator was Eniac, or Electronic Numerical Integrator and Computer, designed and built in the mid-1940s by John Mockley and J. Presper Eckert.
Well, the Eniac was built at the University of Pennsylvania. We started work on it in 1943, and we finished it just a little under 3 years later. It was quite large. It occupied a 30 by 50 foot room. It weighed 30 tons. It had over 40 panels in it. And it had about over 18,000 vacuum tubes in it. This would be enough to build 1,000 television sets today. The machine was primarily and originally built for ballistics calculations, but one of the first important things we did with it was to prove that that electronic computers could be used to solve nuclear physics problems. And we did a feasibility study of using an electronic computer to solve problems of this type, which couldn't be solved any other way at that time on the Eniac. In about 2 weeks, during which we had maybe a dozen hours of actual calculation, we did work that would have taken a man with a desk calculator 100 years.
This is J. Presper Eckert, now a vice president of the UNIVAC Division's Presper RAND Corporation.
Well, I think the first reaction that John and I had when we stood in the midst of these many panels and saw some 3,000 little pink lights flashing all around us was as if we and the other people had been involved in building a sort of cathedral. I mean, we were impressed by the appearance of what we had done more than anything else.
With the addition of electronics to our calculators, we increased our speed, our brute force speed, by a factor of at least 1,000. But perhaps the greatest advance of all was the concept of storing instructions within the machine in the same way that we stored data. This is the concept due to John von Neumann. Now, since the time of the invention of the stored program concept, as we now call it, we have gained many other things, but they seem relatively small. The introduction of mass production, increases in speed, reliability, and lowering of the cost. All of these pale into insignificance in comparison with the stored program concept itself. A computer, as we know it today, is a device which can accept information in some form, store it, process it, and produce answers in an acceptable, readable form. With this definition, of course, goes the injunction, if we're going to call it a computer, that it must be able also to store its own instructions and process them from within the machine.
The idea of the stored program, developed by John von Neumann in the late 1940s, is one of those simple, beautiful, and very powerful ideas. If a machine can store numbers, why not have it store instructions in the form of a number code? The modern digital computer stores both data and instructions in number form. It does this by converting all the information fed to it into a two-state or binary number system. Under the binary system, any known number can be expressed by some combination of ones and zeros, and letters and other symbols can also be expressed by ones and zeros in accordance with a prearranged code. The two digits 1 and 0 can be represented by the physical state of the electronic circuits in the computer. That is, Voltage on can stand for 1 and voltage off for 0. In the electronic memory of a computer, these digits are usually expressed by the direction of a magnetic field set up in tiny metal rings or cores threaded on wires. Magnetized north can mean 1, magnetized south can mean 0. These individual digits are called bits, a term coined from binary digit. A combination of bits makes up a computer word, and the size of a computer's memory is determined by the size and number of words it can store. The data or numbers and the instructions in number form according to a specific code are identified in a computer memory by means of their electronic locations or addresses. A computer will go from address to address in strict sequential order unless instructed to jump or branch to a given address. When branching is dependent upon the outcome of a particular calculation, we have a form of decision-making. A computer can also be instructed to move the address of an instruction. In this way, it is able to modify its own instructions and to operate at an even greater level of sophistication. We are moving into a world where computers will do many of the things we have long associated with human problem solving. Tasks involving the making of complex decisions and the control of other machines and processes. And our children will have to know much more about this technology than we do. From teaching experiments that Fred Gruenberger and others have been conducting, we know that younger minds do not have the same resistance to the complex language of numbers natural to computing machines that so many of us may have. For young students, there is a wonder and a delight in learning how to use a new and exciting tool. For many youngsters, the rigors of logic and mathematics hold no terrors, and they are able to master in a surprisingly brief time the rudiments of using a computer to solve difficult problems.
I find it delightful to let students consider this problem a little and perhaps ask their teacher how it works. Now, the last problem on the tape here illustrates again something else. Our problems are getting a little bit more complex as we go along. Can you tell me what this one does? We get the numbers 3, 4, 5 on a line, then 5, 12, 13.
Those are Pythagorean numbers.
Right.
I took number 30 years ago.
They are integers which can satisfy the Pythagorean relationship. Let's stop it a second. The last line we saw here, 63, 16, 65, would satisfy a right triangle. 63 squared plus 16 squared would equal 65 squared. Let's just let this run a little bit more. I'd like to use this last problem as an example of the thing we were talking about before. How do we get a computer to do a job like this for us? I remember we were talking about the four-way test of putting a problem on a computer. Remember the 4 points. Is the problem defined? Is there a way of doing it? That is, does a method exist? Will it fit the machine? And is there a payoff? Now, the problem is well defined, in this case, even for a high school student. He has perhaps experimented with the first 3 or 4 lines of this table. He's obviously run across the 3, 4, 5 triangle in his geometry book and in class. He's probably never seen the triplet 91, 60, 109.
Right.
But at least he knows what the problem is, therefore it's defined. Since we are generating them, it's obvious to us now that there is a method, but it wouldn't be obvious to a high school student that there is a method of getting all of them systematically. The numbers involved here are small, and the logic of the problem is very small.
Let's for a moment look at a somewhat more commonplace problem than the generating of Pythagorean triplets. How may a computer used by a banking firm be instructed to do accounting operations and to decide whether or not a particular account is overdrawn? The mathematics of the problem is simple enough. An accurate record of the amount of money in the account must be kept, and the checks that are written must be charged off against the account. It's a matter of record keeping, addition, and subtraction. However, a computer is a know-nothing machine until it is instructed to perform the required calculations and decisions. Planning this sequence of steps for a computer to solve a problem is part of the job of the human programmer. He will draw up the sequence of steps in a form called a flowchart. A flowchart, just because it must contain every step that the computer must perform, can become very complicated. But if we examine one small section of it, we begin to see that indeed a computer does things in small steps, but it can also make decisions as to which of several alternative steps it should take. This is a simplified flowchart detail for that portion of the data processing operation where a check drawn on an account is posted against the master record for the account, which is on magnetic tape. The computer will make a decision by testing whether the account balance is negative or positive. If the balance is negative, it means that the account is already overdrawn. The computer will then add 1 to its record of the number of times the account has been overdrawn. It will then store or electronically file this new information. Next, the computation is required. Is the amount of money sufficient to cover the check which is being processed? The computer compares the amount of balance with the amount in the check. The answer is yes if the balance is larger. The computer will then deduct the amount of the check from the original balance and will print out this new information on the customer record. However, if there are not sufficient funds to cover the check, the computer will record this information, write an exception message, and print out the appropriate customer record. This tiny section of a flowchart represents only a very few of the many steps and decisions made at lightning speed by a computer in what is called demand deposit accounting. However, the detailed instructions on the flowchart cannot, in their original form, be communicated to the machine. They must be translated into number form, the only language which the machine can handle and understand. And the machine language, or code, is different with different machines. Fred Gruenberger describes a portion of the coding or machine instructions for the problem on Pythagorean triplets.
This is a sample of the code taken from this specific problem. We're taking just one little portion of the problem and showing the 7 machine instructions which implement it inside the computer. The language we use, of course, relates to this specific machine and would be different on another machine. Since each of these instructions is 12 digits long in this machine, they are located somewhere in storage at areas that are 12 digits apart. Actually, the 1012 here refers to this digit within the machine as a matter of convenience. Now, I'll translate them as we go. The details are not too important, but people are interested. The question was, is R odd? And we used the idea that if we multiply an odd number by 5, the final digit of the product is a 5. Otherwise, it would be a 0. So this says to the machine, multiply the number called R, which we have put somewhere else in storage, not in this area, of course, up here at 10,005, by the number which is right in front of us here, the number 5. Multiply R by 5, and in remarks, we say what we're doing. Now, the next thing here is a detail of machine coding that doesn't seem to be part of the logic of our problem, but these are things that have to be done. We're going to get a rather long product. We want simply to look at the last digit. In this machine, we have to fix it up to be a 2-digit number. So what this says is put a 0 right next to the last digit. All right, now we're back to the logic of our problem. This says to the machine, compare the 2-digit number. This should be at 99, not 98. Well, that's how things go. It's easy to make a mistake like that, to get 1 digit wrong. And this sort of thing would make the whole problem collapse. If we went on the machine with these actual instructions now, we'd be in quite serious trouble. We'd get an overflow, the machine would stop, and so forth. This should be a 99. Compare the 2-digit number now located at 99 with these 2 digits 0. The logical question is R even? Are its last 2 digits now 0? Now here we come to the feature which makes the stored program computer such a powerful tool. The factor of 1,000,000 you were talking about was a brute force factor in actual speed. This is the factor which gives us computing power. We have now the ability to branch. Normally the machine will execute these instructions one after another in sequence, but occasionally we want to make one of those two-way choices that we saw on the flow chart. This says to the machine, go to the instruction at 1084 if. And the if here is a coded number, meaning if the comparison we just made here came out to be equal. And we've drawn it here on the code with arrows. It says do not advance in the normal way to 1060 if that condition was met. If it is not met, do advance in the normal way. Now, a beginning student is usually rather impressed with the tremendous amount of detail which we have to use to implement such a very simple concept. Is R even or odd? It seems very easy. And it's taking us 7 instructions, each of 12 digits, each of which had better be correct in every digit, or we're going to be in trouble, just to get this one little part of the problem done. And as we saw before, the whole flowchart of the problem is quite long. It's going to take a considerable number of instructions, perhaps as many as 150 for this problem, just to get this flowchart implemented into computer code.
And we spoke in the language of numbers and reached understanding. The nature of things is number. This statement can be traced to Pythagoras and his followers. In truth, everything that can be known has a number, for the nature of number is the cause of recognition, able to give guidance and teaching to every man in what is puzzling and unknown. For none of existing things would be clear to anyone, either in themselves or in their relationship to one another, unless there existed number and its essence. Today, our interest is not in any mystical value associated with number. Rather, it is in the use of number as a means of extending our understanding and control. And computers, these machines that extend our intelligence of things, bring the vast universe of number within our reach, in controlling what we choose to control, in predicting what we seek to predict, and in planning those great works of the imagination that may take us into worlds beyond our own.
Roger, 0G, and I feel fine. Capsule is turning around. Oh, that view is tremendous.
This is NET, National Educational Television.